quantum mechanical model of the atom, the Bohr model of the atom. In this tutorial, we will be going over the Bohr model of the atom, of course, and the Bohr electron configurations and how they relate to the periodic table. Prior to the adoption of the quantum mechanical model of the atom, which we will talk about in the future, Ernest Rutherford proposed a planetary model of the atom. In this model, the majority of the atom's mass was found in a positively charged nucleus, as we can see right here, surrounded by negatively charged electrons. The attraction between the positive protons and the negative electrons can be conceptualized through Coulomb's law. According to Coulomb's law, the force between two charged particles, Q1 and Q2, is inversely proportional to the square of the distances between them, r squared. If the two charges have opposite signs, the Coulombic force is attractive. If the two charges have the same sign, the Coulombic force is repulsive. After heating various elements, Niels Bohr observed the emission, again release, of electromagnetic radiation. When this electromagnetic radiation was observed using an instrument called a spectroscope, a pattern of spectral lines, atomic spectra, unique to a specific element was observed. Bohr attempted to explain the atomic spectra phenomena by building upon Rutherford's model. Bohr proposed that electrons travel around the nucleus in circular orbits or electron shells. These orbits exist only at specific fixed distances from the nucleus. The energy of each orbit is fixed or quantized. So what we are seeing over here in this PhET simulation is our positively charged nucleus in the center, and each of these dotted circles that we see around the nucleus are representing our electron shells. And then ultimately, this blue dot that we see jumping all over the place is our one electron associated with a hydrogen atom. When an electron transitions from a lower energy orbit closer to the nucleus to a higher energy orbit farther away from the nucleus, which we know as the excited state, energy is absorbed by the electrons. Spectral lines are only observed when an electron transitions back to the original lower energy orbit closer to the nucleus, which we know as the ground state, releasing the exact amount of energy absorbed. So what we can see from this PhET simulation is that this electron closer to the nucleus collides with a photon, jumps to a higher energy level, and then returns back to the ground state. We can see this in this electron energy level diagram over to the right, where electrons are absorbing energy and then falling back down to ground state, showing the electron moving from the ground state up to the excited state and then back down to ground state. Bohr electron configurations and the periodic table. Electron configurations provide information regarding the approximate location of electrons relative to the nucleus within a given atom and the approximate energy associated with a given electron. The total number of orbits or electron shells of an element corresponds to the number of the period, and we know that the periodic table has periods 1 through 7, where that particular element is located. Orbits located farther away from the nucleus have a higher energy associated with them relative to the orbits located closer to the nucleus. So here we have a shell diagram of potassium. So the electrons found closest to the nucleus would have the lowest amount of energy, and this valence electron out in the farthest shell would have the highest amount of energy associated with it. The maximum number of electrons possible in a period on the periodic table is determined by the relationship 2n squared, where n equals the orbit electron shell, number 1 through 7. So in period 1, we have one electron shell. We'd put that 1 in as n, so 1 squared is 1 times 2, which means the maximum number of electrons in the shell is 2. For period 2, n will equal 2. 2 squared is 4 times 2 is 8. So the maximum number of electrons in this shell is 8. Period 3, n equals 3. 3 squared is 9 times 2. Maximum number of electrons, 18. The Bohr electron configurations follow the 2n squared relationship for the first 18 elements, ending with the element argon. Based on this pattern, the Bohr electron configuration for potassium should be 2, 8, 9. However, the Bohr electron configuration for potassium is actually 2, 8, 8, 1, and this is even seen on your New York State periodic table. The Bohr electron configurations for the elements of period 4 and beyond do not seem to follow a predictable pattern in terms of electron placement for the 4th through 7th electron shells based on what you have learned previously in this class. Consider the following period 4 elements and their Bohr electron configurations as can be found on your periodic table. So calcium is 2882, scandium is 2892, titanium is 28102, vanadium is 28112, and then weirdly enough, chromium is 28131. Electron configurations associated with the quantum mechanical model of the atom provide insight into the deviation from the 2n squared relationship observed with the Bohr model electron configurations. So our goal for the next video is to figure out why this deviation is occurring, and this will be examined in depth in the future. So what did you learn? We did a review of the Bohr model of the atom, which you should already know from Regents chemistry. And then we looked at the relationship between the Bohr electron configurations and the periodic table. Need more help? Feel free to contact me. Have a great day.